We're going to go over 8.2 and we're going to find arc length. So we did that last video, but we're still going to be doing it this video. But this time we're going to use radians, and then we're going to find sector area. So to start us off in our warm-up, I want you to take out your unit circle. So you may have to pause the video and go grab that. And then I want you to convert every angle on your unit circle into radians. So again, you may want to pause the video and go do this, but let me get you started. So 0 is easy because 0 degrees or 0 radians is still the same. So let's go to 30 degrees to start us off. If I was going to convert 30 degrees on my unit circle, I would take that degrees and I multiply it by pi over 180, and then I'm going to simplify. So remember, we would numerator to the numerator and denominator to denominator. And I know 3 goes into 18 6 times, so 30 must go into 180 6 times also. So that means we're just left with pi over 6, which means on my unit circle, which here's an example of a unit circle, I would go to my 30 degrees, and I've already got my ordered pair next to it, and now I want to add radians. So the radian measure at 30 degrees would be pi over 6. So I want you to go through and convert all the way around your unit circle, all of these measures, and then come back and check and see if you did those right. All right, so here, let me just fill in the rest of the radians for this unit circle. So at 0 degrees, we just have 0 radians. It's still the same. But let me progress around. When we get to 45, when you simplified that, it should end up to be pi over 4. At 60 degrees, we should have got pi over 3. At 90 degrees, pi over 2. At 120 degrees, 2 pi over 3. At 135, 3 pi over 4. At 150 is 5 pi over 6. 180 would just be pi. Those 180s would divide each other out. 210, we get 7 pi over 6. At 225, we get 5 pi over 4. At 240, we get 4 pi over 3. At 270, we get 3 pi over 2. At 300, we get 5 pi over 3. 315 is 7 pi over 4. And then at 330 is 11 pi over 6. And then when we get full circle back to 360, it would just be 2 pi. So let's just talk a little bit about patterns for a second. We would see similar patterns that we saw before, but let's maybe start at our 30 degree angle. If we know 30 degrees is pi over 6, our next 30 degree angle would be 60. So really we'd be taking 2 pi over 6 when we got to this location. Well, 2 pi over 6 reduces to pi over 3. So we have 1 pi over 6 at 30 degrees, 2 pi over 6, which reduces to pi over 3. And then when we get to the next one, we'd end up with 3 pi over 6, which would end up to be pi over 2. And we can keep going around the whole unit circle like this. Our next 30 degrees, we had 1 pi over 6, 2 pi over 6, 3 pi over 6, and we get to 4 pi over 6, which 4 over 6 simplifies to 2/3. Then we get 5 pi over 6, which doesn't simplify. And then we get 6 pi over 6, which ends up to be pi. And we can keep going around the whole unit circle like this. Same thing can be done with your 45s. If 45 is pi over 4, then 2 pi over 4 ends up to be pi over 2. 3 pi over 4, that one doesn't simplify. 4 pi over 4 simplifies at 180. 5 pi over 5, or 4, that's not going to simplify. And again, that just keeps going around. So similar to when we memorize the unit circle, you don't have to memorize all the way around because you should be able to figure them out. So we're going to keep this handy because we're going to need to use this now for our radian measures a little bit. So let's go ahead and go back to our notes. And it says below the warm-up that in the last section, we learned how to find arc length when we were given a central angle in degrees. So you also learned how to convert angles into radian measures. So now we're going to find arc length using those radian measures for our central angles. So we're going to need to convert our formula from degrees to radians. So just like we converted anything else, we're going to have to multiply. So if our arc length had a pi in it, that means we want to get rid of that because our theta is going to have our radian in it already. So by multiplying by 180 over pi, those pi's are going to divide out. So will the 180s. And our theta, which is now going to be in terms of radians, will have our pi in it times our radius. So this time, as we look at example 1 and we're trying to find arc length, we just have to take the radian times our radius. So example 1 wants us to draw again. So theta wants us first to draw 5 pi over 3. Now this is super new to us, so you're not going to probably remember where 5 pi over 3 is right away. But if you look on your unit circle, you should be able to see where you labeled 5 pi over 3. If you don't end up to have your unit circle, then you know that you could always convert this by multiplying by 180 over pi, and that will convert it to degrees, which I believe is 300 degrees, which then you could approximate maybe a little bit better on your circle. So if you've got your unit circle, you can use it. If not, you could always convert it. So that 5 pi over 3 we'll say is like right about there. Now remember, this is a rotation, so we're rotating from that positive x-axis the radian measure of 5 pi over 3. And we've got a radius of 3 centimeters long. So how long is that arc? So the length of our arc when our theta is in radians can be found by taking theta times the radius. My theta, 5 pi, over 3 times that radius, I'll put that in parentheses, times 3. Now the directions do want us to round to the nearest thousandths on this one to get our length. I do notice that my 3's will divide out, one in the numerator and one in the denominator. So when I go to use my calculator, maybe I just put in the 5 pi and have it approximate that for me. So the length of this radius, or excuse me, of this arc should be about 15.708, because that 9 will round my 7 up. So I'm going to change that to an about since we're approximating here. 15.708 as that rounds. And then please put our units when we're given those. Okay, let's try it again on B. So again, we don't know this probably as well, but 2 pi over 3, when we're trying to think about what that is, we can use our unit circle, or again, we could multiply by 180 over pi and come up with our degrees, which would end up to be 120 degrees. But if we've already looked on our unit circle, we already have an idea of where 2 pi over 3 is. So now to find that length. The length of that arc can be found by taking the radian times its radius, which is 12 in this case. That was a bad pi. Let me try that again. So again, my 3 and my 12, I can at least maybe simplify that a little bit before I put it into my calculator, or if you just want to put the whole thing in there. I know it's going to give me a decimal. It's got pi in it. So I'm just going to go ahead and take 2 times that 4 and call that 8 pi, just for sake of putting it in my calculator. So 25.133. So 25.133, and this is in meters. So that would be a pretty big circle if that was in real life. Okay, so really a similar process. We just, because our theta is not going to be in degrees, then we just alter our equation a little bit. Because our theta is going to be in radians, it's already going to have that pi value in it. Okay, the next thing we need to talk about is sector area. So as it says below, a region of a circle determined by 2 radii and the arc intercepted by the radii is called a sector of a circle. So in parentheses, I put think slice of a pie or slice of pizza or something. That's what we're talking about when we call it a sector. A sector is a fraction of a circle. So the ratio of the area of the sector to the area of the entire circle is equal to, and I've kind of got some fractions started down here, area of the sector compared to area of the circle is equal to the measure of the central angle that's creating the sector to the measure of the entire circle. So we're going to take this ratio, area of the sector compared to area of the circle, and the ratio of measure of the central angle to the measure of the circle, and we're going to give us some letters here. So let's call the area of the sector A for area. And we know, or should know, the area formula for finding the area of a circle, pi r squared. The measure of our central angle, we've been using theta, so I'll go ahead and call that theta. And the measure of an entire circle is 360 degrees. So there's basically our ratio. And if we're going to try and find the area, that means we need to cross multiply this and solve for A. So I'm going to go ahead and do A times 360, but I'll put that 360 in front of the variable. And then we have theta times our pi r squared. So if I divide both sides by 360, I have theta pi r squared, and that's going to be divided by 360. So if I want to find the area of a sector, a piece of a pie, a piece of a pizza, then I can use this formula. So below, let's put this a little bit nicer. If our angle is in degrees, then the area of a sector is, so I've got capital A already written, is equal to, and we're just going to write this just slightly different. We're going to take our theta and our pi and put those in the numerator over our 360, and usually we see that radius squared to the side, just like we saw with arc length yesterday and today so far. Well, if we want to find the sector area, if we're given a theta in radians, then we just have to convert our formula. So we're going to take that area formula, that theta pi r squared over 360, and we're going to multiply that by 180 over pi. So again, radians already have a pi in its measure, so we don't need two pi's in our equation. So our pi's will divide out. 180 and 360, that's going to leave me with a 2 down here. So really I end up with a theta r squared over a 2. So we're going to, again, just kind of rewrite this a little bit nicer. If our theta is in a radian measure, then the area of a sector can be found by taking, so A is equal to, we're just going to call this 1/2, because that is our theta, which will have our radian in there, our pi value, times r squared. So here's our two formulas for helping us find area of a sector, and it'll just depend on which information we're given. So let's go ahead and turn to the second page. Example 2 wants us to find the area, and we're starting with degrees. So we're going to find the area of a sector if we know the radius is 5 and the angle that we're looking at is 135. So our formula from that front side, maybe I can still see it here. Yeah, in degrees, we want to take theta times pi. So I'm going to go ahead and write that. Theta is 135 times pi, and that is over 360. And we're going to multiply that to our radius, which in this case is 5 squared. Now, you can try and simplify a little bit before you put it in the calculator, or you can put it all in the calculator however you want to. I'm going to go ahead and just put it in as a fraction. 135 pi over 360. And I'd like to multiply that by my radius squared. So in this case, it's going to give me, we're going to still do the same decimal approximation here. We've got about 29.452. We wouldn't need any rounding on that. So this is going to be about 29.452. And technically this is area, so we would remember that this is square units when we're talking about this area. Let's try it again on B. area is going to be equal to our theta, which is 120, times our radius over 360 times that radius squared. So again, we could try and simplify a little bit if you want to, or you can go right to your calculator and put in that fraction. 120 pi over 360, and we want to multiply that by 10 squared. 104.719. So that 9 is going to get rounded up because we've got a 7. So I'll call that, and then that will round up to a 2. So 104, whoops, I forgot my about. So this is going to be about 104.720, I'll call that. And this one was meters, so meters squared. So this finds the area of a sector given that our theta is in degrees. So let's practice in our next section. Example 3, and let's convert, it says, each degree into radians. And then we're going to find the area of each sector using those radians. But notice it says to leave our answer in terms of pi. So we don't want a decimal approximation on this one. So the first thing I do is have to do some conversions, which if you've got your unit circle and you've already converted it, then you're welcome to look there. But 60 can be converted into radians by multiplying by pi over 180. And 60 goes into 183 times. So that gives me a radian measure of pi over 3. And now I have what I need to plug into my equation. So my equation we found would be 1/2 of that theta, which is in radians, I'll put that in parentheses, times our theta, times our radius, which in this problem is 4. So 4 squared. Let me scoot that up a little bit. So I'm going to go ahead and think about simplifying it. You could put it in your calculator, but remember we don't want this pi to go away, so it may be helpful to kind of think about it in our head. So really this is a numerator, this 4 squared. So 4 squared is 16. 1 times pi times 16 would just be 16 pi. And then in our denominator we have 2 times 3 times 1, which can be simplified because both are divisible by 2. So we'd end up with 8 pi over 3. And this is still area, so we'd want our units, and in this case, inches squared. Let's try that again on B. 120 degrees, if I didn't have my unit circle handy, can be converted into radians by multiplying by pi over 180. So we end up with 120 over 180, and both of those, I believe, are divisible by 60. So we end up with 2 pi over 3 as our radian, and our area can be found of this sector by taking 1/2 of that radian times the radius squared, and our radius this time is a 2 squared. So again, I probably wouldn't use my calculator too much. We can just simplify across our numerator. So 1 times 2 pi, so 1 times 2 pi times 4, 2 squared is 4, 4 times 2 would be 8. So we end up with 8 pi, and then our denominators again are 2 times 3 times 1. So when we simplify, both of those are divisible by 2. So 4 pi over 3. And this time our units are feet, so feet squared, because we're finding the area of a circle, or a sector, excuse me. All right, so go ahead and self-assess. How do you feel about finding the sector area now, and also just still computing that arc length? And good luck on your assignment.